All right, hello everybody. Recording a little lesson today, online again. Hopefully you are okay with this format. Hopefully you don't speed me up to 2 times so I sound like a chipmunk. Uh, Hopefully you take your time and kind of work through the examples as we do them and try and get that same experience we would get if we were in a classroom. I'll try and make it as non-boring as possible. The topic of the day is energy. That's kind of our week 3 content. But before we jump right into that, I just want to back up. I'm going to try and do this every week. Let's just backtrack and remember what we did back in week 2. Week 2, we learned about Newton's laws and Newton's forces. Let's say, let's say we have a thing sitting on the ground, maybe a kid on a toboggan. It's a nice snowy day. 10-kilogram kid sitting on a toboggan. You pull it forward. I'm going to call that F applied with a force of 30 newtons. And there's a coefficient, there's friction. The coefficient of friction is 0.2. So there's a backward force of friction. I would like you to figure out the acceleration. So if this were like an assignment or a quiz question, I would do a lot of typing, but just kind of out loud. We got this 10-kilogram thing. You're pulling it forward with a force of 30. There's a backwards force of friction because there's a coefficient of friction of 0.2. And I want you to figure out the acceleration of this thing. Kind of whenever a question has a mu, we only have one equation for that involves the mu, and that's FF equals mu Fn. So whenever a question has a mu, we have to get the Fn. There's no way to kind of work with mu without knowing Fn. So the starting point for this question is we're not going to jump right into what's happening left, right. We're going to look at the up, down. There's going to be gravity acting on this thing, and gravity's mass times 9.8. And at Newton's third law of reaction force, there's going to be this upward force acting on it. This one was called the normal force. It's kind of an answer to gravity. It's what the surface pushes back up on the object to keep it from falling through the ground. The way this one is worded, it doesn't say anything about this being in an elevator. We did some elevator questions last week. It doesn't say anything about it being in a rocket blasting off. So basically, forces-wise, that means the normal force is canceling gravity. If normal force were bigger, it would be accelerating up. If gravity were bigger, it'd be accelerating down. Since it doesn't say anything about up or down, I know that the up and the down forces completely cancel, or the normal is equal to gravity. In the horizontal, we've got what I'm going to call a tug of war. We're going to set up F net equals ma, Newton's second law. We've got this F applied, that's our winner force, that's the one that's making it move, so I'm going to make it the positive force. In our tug of war, our loser force is friction, and that's equal to ma. Kind of what I doodled over there, the whole point, FF is mu times Fn, and that's equal to ma. From what we talked about up here, a little messy, we know what Fn is, so really this turns into Fa minus mu mg equals ma. We see this one quite a bit. Just forward minus backward equals ma. Backward turns into friction mu mg. This particular question we're doing to warm up, we're trying to figure out the acceleration. So at this point, we know everything but the a values, so it's what I would call a plug and chug. Let's just stick our numbers in. The F applied I made up was 30. The mu was 0.2. The mass was 10, and the g was 9.8. M was 10, so we get something like that. That turns into the 30 still there. The 0.2, the 10, the 9.8. Have your calculators at the ready. Make sure I don't goof this up. I'm getting 19.6 for that, equals 10a. 30 minus 19.6 is pretty close to 10, so we're going to have 10 divided by 10 when we do our algebra. It's going to be really close to 1. I got 1.04. It's an acceleration, so it's in those funny units of meters per second squared. All right, that's just a quick little recap of what we did last week. Hopefully that one made sense and you can handle that. Jumping ahead, week 3 is all about energy. I don't want these videos to get too long, so I'll talk a little bit more about energy. Then I'll stop this one and I'll restart another video for you to just sort of cycle through. If if we were together and we were in the classroom, I would ask you guys to talk about it. When the word work, that's a word that shows up in everyday life. Like if you've been alive as long as you've been alive, you know the word work. You know what work is. You can do work. You've done work. You have an idea in your brain about what work is. Unfortunately, this is one of those cases where the definition that you put together in your brain from being alive might not exactly match exactly perfectly what the physics definition of work is. The physics definition of work is if you put a force on something, it's two-part. You put a force on something and that force makes it move. If you do that, then you've done work on the object. If for some reason somebody gives you something heavy to hold on to, and you're just standing there holding on to this heavy thing, using your arm muscles, just holding it and holding it and holding it, you're putting a force on it. Your arm muscles are putting a force on it so that it doesn't fall. But if you don't actually move it, if you just stand there and hold on to it, then you haven't done both things. You have to put a force on something and make it move. If you do that, then you've done physics work on it. Another way to think about work, this might be more helpful. If you do work on an object, then you increase the energy of that object. What's dicey about this equation is now I'm linking the physics word work to the physics word energy. If you have a good understanding of energy, then that definition might be helpful. But we might not have a great understanding of energy yet, so that latest definition may not be quite helpful yet. But we're going to talk a little bit more about energy, so we'll circle back to that one. If nothing else, we can start playing around with numbers and doing examples, like practicing it out. Work is going to have an equation. Work is all about force and motion, a force making something move. So the work equation is force multiplied by distance. And then because sometimes vectors and two-dimensionally, there might be an angle involved. So it's also multiplied by the cosine of the angle. The angle that we're cosigning is the angle between the force and distance. We'll do an example to clarify that. If we short form that down, physics people wouldn't want to write work equals force times distance over and over again. If we short form that down, our equation for work, short form for work is going to be capital W. Short form for F, we saw that before, capital F. Short form for distance is letter D multiplied by the cosine of X. The metric unit for work, one of my favorite metric units. Force we talked about, force is in newtons. Distance we talked about, that should be in meters. So technically the unit should be newtons times meters. Cosine of X doesn't have a unit, so it's just newtons times meters. Technically it should be in newtons times meters, but they named it after a cool physics guy whose last name was Joule. So the metric unit for work is joules, or capital J for short. This guy, James Prescott Joule, he was basically he was a rich British guy. His parents owned a brewery, so he didn't really have to work because his parents had made all the money with the brewery business. So he's just hanging out in the brewery all day. Um, I imagine. I kind of, in my brain, I picture him having a couple pints and he's thinking about physics. And basically, he uses the brewing vats, the brewing equipment, to figure out how heat kind of connects to energy. He did these crazy experiments where he would stir the water and then measure temperature change in the water. Yeah, so James Prescott Joule figured out how heat connects to energy, so they named the unit after him. Everyone's going to recognize the older non-metric unit for work. If we were in class, I'd get you to guess or see if someone could come up with it. This one is the calorie. Oops, calorie. Now, when you look at a menu and it mentions how many calories are in that burger you're about to eat, it's telling you the energy content. Also named, I'm not sure if it's named after a person, but that's the old one. And another one that you'll see in the everyday world, we're not going to use it too much in physics, but another non-metric unit for work or energy is the kilowatt hour. If you're shopping for appliances, often appliances are kind of rated on how much energy they use, but instead of putting that energy in joules or calories, they put that energy in kilowatt hours. All right, let's jump in and do a couple examples just to make sure this kind of clicks. All right, this one I'm gonna emphasize this angle business. So let's say we've got flat ground and a person's pulling their suitcase and they pull it straight sideways. They're dragging it maybe down an airport and we're told that they pull it 250 meters. But because it's one of those wheelie suitcases, they're actually kind of pulling it up and on a funny angle. They're pulling it this way. At a 30-degree angle above the horizontal. That's what I meant when I said the angle was between the distance and the F. If we put the distance and the F at a common starting point, if there's a funny angle between them, that's the angle that goes into our work equation. Work equals FD cosine of X. That equation will be typed on our equation sheet. You'll be given it on quizzes and exams, that sort of thing. The force is 15. The D is 250. And then we got to multiply that by the cosine of 30. So I'm going to calculator out and double check it. I'm getting 3,248. That turns into those cool units of joules. If we're going to be nitpicky, I'm not going to be too nitpicky, but I'll try and just do it at the end of every question just in case it comes up in other courses. We should round this one back to 2 digits. So 3,200 joules, or if you want to get really fancy, 3.2 times 10 to the 3 joules. I'm not going to get too picky about digits. My main goal is that you understand the physics of it first, and then we'll work on digits and notation as we go. If you agree with 3248, that's where I need you to get to for now. I'm going to pause this video just so they don't get too long and clunky, and then we'll start another one.